Hi everybody, welcome back. Well, here's the newest addition to the bench, and I think it'll be very useful for certain things. And what this is a Sencore model PA81 power amplifier analyzer. It's basically a fancy resistive dummy load for amplifiers. But it does more than that, and that's what makes it kind of cool, because a couple of the ideas that I had that I wanted to implement into my speaker load that I have on my bench are actually implemented in this. And that is the ability to measure the wattage directly, the ability to put full power into the amplifier, but actually listen to it with my ears at a reduced volume, and to have an external output to go to an oscilloscope so I can visualize things, or to connect external test equipment without actually messing around with the grounds and everything. So this is actually capable of doing all of those things. It has internal non-inductive resistors, and it can put anywhere from a 2 ohm to a 32 ohm load on your amplifier. It's stereo, so there's two of everything, and it can handle up to 250 watts. Now, of course, it can't continuous, but for a test it can go that high. It has fan cooling that, and like an air tunnel that actually brings cool air across the big load resistors to cool them, and it even has temperature monitoring. And it can do a bunch of other things that are really useful. Like, for instance, it has a DC balance detect. So if you have an excessive amount of DC offset on your speaker terminals, these lights will come on and tell you that there's DC offset. And there's even a relay in there that will disconnect the device from the amplifier when it sees that. And then you would hit this button to reset that. You can actually measure increases in dB, from a set reference by setting up, a reference signal and then hitting reference store, and then it'll measure the increase in decibel of power or whatever. It has different ranges, so you can actually change the sensitivity of the meters. It has input filters, which is really cool, because you can filter like a band pass, which like between 200 hertz and 15 kilohertz, and it'll roll off everything above and below that into the into your it doesn't do that to the load, but it actually does that to the meter. So you can actually, if there's like subsonic noise or something, you can filter that out. Same thing with high pass, anything above 200 hertz, it'll only measure that. Or low pass, anything below 15 kilohertz, or anything below 30 kilohertz. Now, you don't always want to use that, because sometimes you want to be able to see if there's like parasitic oscillation or something taking place like that. But you can actually measure the actual output within a frequency range. So it does a whole lot of things. It has built-in speakers on each side. There's a speaker over here, one on each side, and of course somebody put this cover on wrong, I can see right now, because these are supposed to be up front. These are the actual speaker grills. There's little speakers inside here, so I'll have to take this apart. I just got it. I don't even know if it works. I haven't plugged it in. It did not come with a power supply. And one of the problems with this is it uses a standard 12 volt power supply, but it uses a barrel connector that's a lot longer than the standard ones you get with the little wall warts that you purchase, like this type of thing. This is the correct plug, but it's too short. It has to be almost double that length for it to work. So what I have two choices. I can purchase some new barrel connectors, or I can go ahead and just change out the connector on the back to use a standard power connector. And that's what I will probably do, simply because I want the ability to be able to plug in a different power supply if the one I have fails. I don't want to have to solder a new barrel connector every time. So let's take this apart and just go over it real quick, and then we'll see if we can get it working. Okay, so getting the top cover off, you just take the back bezel, which is just a bunch of screws all the way around, and then the cover, there's a top and bottom, they just come right off. Very easy access. The big power resistors are inside here, and I can see there's a broken screw right here. This has obviously been worked on in the past. I don't know that it's been repaired, but it's at least gone through a calibration or so. But it looks very clean. Look, there's no dirt or dust or anything. Now you may say this is a pretty simple design, and by the way, it did come with the old NiCad battery, or the lead acid battery, I'm sorry. And I think you can still get these batteries, or you can get a similar case style without this top cover on it and make one, but I will never run this on battery. So I will leave it out because all batteries can do is leak or cause problems, so I don't need that. But it's kind of cool that it came with an original battery. Here's the little speakers I was talking about. They're tiny. They're only like, you know, about that big around, but they actually allow you to listen to a sample of what this, you know, the amplifier is putting out into the dummy load. I'll take this shield off and we can take a look at the resistors. Hopefully they're the big thing. I mean, obviously you can order resistors, but they're never going to be these ones. They're special design, and they are made by Dale, which is a pretty common resistor manufacturer, but I think they're special ones, and I think they would be pretty hard to find today. So let's take the cover off and see. So taking the cover off, we can see the resistors seem to be in really good condition. They don't look hot. They don't look like anything has ever, it doesn't really look like it's been used much. You look at the fan, there's no dust, anything. So I don't think this thing's had a lot of use. This relay, I'm not sure, but kind of zooming in on it a little bit, I see solder on top of the normally closed contacts. I don't know if that's just, you know, they soldered this on too. It looks to be factory, and we won't know what the condition of this relay is like until we test it. But this is a pretty common 2-pole 12-volt coil relay that I think if I did need to replace it, I could find it. I probably have those in stock, so I'm not even worried about it. So it looks clean. Now you might think this is a pretty simple thing because these go for a lot of money online still in good condition like this. And you might say, well, there's not much there for how much people are charging, but then you have to look at the underside. Let's look at the underbelly of the beast. Yeah. And this is where it starts to get crazy. Now, there's a lot of, there's an Intel processor on there. And, you know, PROMs and firmware and all kinds of things going on. Typical Sencore, you know, just over-engineered to the max. Okay, well, I guess the first thing to do is determine what we're going to do with the power connector. And I'm sure it's something special and custom also, and of course it is. And there it is in there. Let's see if we can zoom in on a little bit, and you can see right there it is. I don't know if that has a switch. I don't believe it does, because if you look, there's only two contacts on it. The ground right there and the center pole. So I think this is something that I could probably replace with a more standardized connector, and that's probably what I'll do, because again, this thing's just not, it's just a weird size. Okay, let's see if this thing powers up and initializes. So I have a 12-volt power supply just connected with some jumpers onto the back of the jack there. You can kind of see it up there. And I'll go this way. Hopefully you can get most of this in view. Yeah, just pretty close. I'll take this light out of here to make it easier for the camera. And let's turn it on. It looks like it's going through some kind of an initializing thing. Alright. Let's see what happens with this. Okay, so I can get ranges here. And you can see it's picking up a lot of noise. I mean, we're looking at very low range. So there's background noise, and it appears to have just turned off. So there's something strange going on here. We'll have to figure out what's going on and why. It could perhaps be something to do with the power supply. I don't know. See, now that I just turned it on, it seems to have settled itself down. Let's let it run for a little bit here and see what happens. I'll just let it sit here turned on. There, it just shut back off again. So something's going on, and we're going to have to figure out what. But at least it kind of powers on. Well, when it comes to making things complicated, Sencore never seems to disappoint. And of course, in this case, they're right up there. So this is the power supply schematic. And as you can see, it deceptively looks simple when you just connect a 12-volt supply here. And it says AC, but really what they're saying is they have an external AC power supply that converts the power to 12 volts DC. So you have a steering diode here, a 1N4004. Everything's very low current in here. There's nothing, this thing does not draw a whole lot of current. It goes through an LM317, which is your standard linear regulator, and it gives you a 12 volt supply. I have schematics for this. There is no alignment instructions that I could find anywhere. I'm sure somebody out there has them, and I'm sure if I did an exhaustive search of the internet I could find something, but as of right now I don't have anything, so we're going to kind of wing this a little bit. It appears that there are several power supplies that this thing uses. There is a 12 volt kind of a master power supply that everything feeds off of, and that's this little regulated here. And you can see if it's this LM317, these are only good for about 1 to 1.5 amps. So 12 volts at 1 amp, I mean it's 12 watts total, is the absolute maximum most you could ever see here. So 12 volts, and then it feeds down here through these steering diodes, through your power switch, through this 3 amp Schottky diode, and into this, and this is very similar to the LC102 that we did. You have this MOSFET, and this controls the power. This bipolar transistor, which is a 2N3904, very basic, is connected to a signal called auto off. This goes directly to the microprocessor, and this is what actually, this is how the software or the machine itself can turn itself off. I think this is where we're getting our problem from, because it'll turn on and then I bet you this will drop out, and that's what's turning it off. But anyway, when you turn on this MOSFET, it allows your 12 volts to pass through here. And there's a little delay by this 470 microfarad cap. And then it goes into this 78L05, and the L stands for low power. So these are the little, they're not in the big TO220 cases. These are little low current regulators. The other interesting thing is the way they're doing this. You see there's an oscillator circuit. It's kind of weird. You could just take these and directly connect them to here, and you would have your power supplies. But number one, you have to have positive and negative, but that can be dealt with also. But if you look, there's a transformer in here. And this oscillator, it's very simple the way it works, drives this little transformer, which then creates an output. There's a center tap, and you have your bridge rectifier, so that gives you your positive and negative voltage, and then two 78 and 79 LO5s for your plus and minus 5 volts. But here's the thing, the reason they're doing this is these are isolated. So you have 5 volt plus and minus regulated to the left channel and 5 volt regulated to the right channel. So you have two isolated power supplies. That's what's really important. One of the downfalls of the dummy load that I use, it's just resistors, is that the grounds get tied together through the oscilloscope. So if you connect an oscilloscope to both the right and the left channel of, of my dummy load, you've just connected the two negative terminals in, together, and they're common to one another. If you have an amplifier that has to have isolated speaker terminals where the negatives are not tied together, like some amps that'll do bridge mode and things, you can't have any kind of common connection between the negatives. And that's what this is doing. This whole thing has two isolated supplies from the right and the left channel circuitry. So this is a good thing, but that's how they're doing it. So these are the main logic power supplies for the left and right channels. Then down here, there's another one, and you have plus 12, plus 5, and minus 5 unisolated. And they're using this 7661 charge pump voltage converter. So what this does is you have an input voltage, you put this capacitor on here, and all it does is it converts the voltage from positive to negative. So we have a positive voltage going out, we have a negative voltage, or positive voltage coming in, and a negative voltage going out. And that's what feeds the negative 5 volt supply here, the unisolated one. So you have 3 plus and minus 5 volt supplies. 2 isolated ones for the right and left channel logic, and an unisolated one for the things that aren't going to be connected to any of the speakers or anything like that. So it's pretty cool how they did it. And then of course you just have a direct 12 volt output right here, and that's fed from this line right here. So it can be a little bit confusing at first, but it makes sense when you work through it. So one of the first things we're going to need to do is, number one, make sure all of these power supplies are correct. And number two, see if the reason this thing's turning off is because our P4 pin 3, which is coming from the logic board, is telling it to turn off. That's what I believe is happening, and why it's doing that we still have to find out. Okay, before I put all the covers back on the resistor network, I just want to make sure all the solder joints are good, and I want to make sure the resistors are all good as well. So each one, so that one reads like a short almost. There you go, 4 ohms, 8 ohms, 16 ohms, and 16 ohms. And that's how it should be. You have a 4, an 8, and 2 16s. And again, 16, this should be 16 also, 16, and this should be the 8, 8, and 4. So the resistors are good, and I figured they would be because everything's so clean. It doesn't look like this has had a whole lot of use, but it looks like it may have been serviced, though. Who knows? So let me put this back together, and we'll move on. Okay, I'm looking at the relay contacts. You can see the normally open ones are not used in this. This is just here to disconnect the speakers from the load, or the amplifier from the load, if there is excessive DC offset. So I'm going to use the Kelvin leads, and I'm going to use the 4-wire connection on the Keithley 197, and we're going to check this side and the other side of contacts. So let's get you up on the meter, and we'll see. We want extremely low resistance. So connecting to the first one, get on the lead better. That's good. So 17 milliohms. I think that should be okay. And let me go to the other side here. Take me a second to get into the terminals because everything's falling on me. And that one's even better. See, 5 milliohms. So the contacts are not brand new, but they are okay. Yeah. Part of this is how good of a clamp I'm getting onto the terminals with my, because the outside of the terminals themselves are a little bit corroded, but the relays are fine. What you don't want to see is, 100 milliohms or so forth. So that's good. Okay, I just thought of something here, and if I'm right, this thing's going to work and it's not going to turn off. And then if this does work, I'll explain why in a minute. So what I'm going to do is I'm going to take my power supply and I'm going to take the leads from it, and instead of connecting it to the power input jack, I am going to plug it into I'm going to connect it to the battery jack. So this is where that battery would normally connect inside. So this cavity here is where the battery slides into, and then this plug right here goes into that connector down there. And that allows this thing to work without an external power supply. Now, let me turn my power supply on. And here we go. Turning on. And notice right away the meters don't deflect funny. You don't have any kind of weirdness, so that's good. Our battery light is lit. Now let's just wait and see if it turns off, because if you recall, within the first 30 seconds or so, it would turn itself off. Let's see if it just stays on now. I have the feeling it will. And I'll tell you why here in a minute. I should have seen it. It's definitely was that idiot thing on my part. But sometimes you have to think things through for a minute before you figure it out. But it's working. I think this is good. And everything appears to be, I hear the little speakers working. We may need to clean these pots. We're definitely going to clean the switches. It's working, at least from what I can see now. Now let's take a 9-volt battery. Let's see here if I have one. And what I'm going to do is, while this is turned on, I'm just going to take a couple of jumper leads and I'm going to connect them to one of these speaker terminals. And I am going to apply 9 volts to the speaker terminals. And I'm going to see if this thing triggers. Let's see what it does. And there it went. See that? As soon as I touched it, reset. So again, there you go. So the DC offset protect circuit is working. Let's try the other side. Clip this on here and let's see. And there it goes. And see, it flashes at you and says, hey, I detected DC on there. So I think this is functional. All right. So now let's explain why. Okay, back to our power supply schematic. And let me get my pointer out here. Okay, so back up to here. When I connected the power supply here, The thing turned on, worked for less than 30 seconds, and then shut back off. And the meters did some funny things too, if you remember. Disconnected the power supply and hooked it to the battery terminals, and all of a sudden it worked. Well, here's why. Although this tells you on the back of it, external 12-volt power supply, and it says very clearly, as you can read down there, well, it says DC input, but it says 12 volts in the book. It's actually not 12 volts exactly. It is an unregulated transformer linear power supply, unregulated 12-volt supply, which is really closer to about 14 volts, 13.8 to 14. And the reason for that is, in order for these linear regulators to work, they have a characteristic called a dropout voltage. Your dropout voltage is the amount of voltage difference you have to have for it to function from the regulated voltage. So, for instance, if we wanted 12 volts here, these have a dropout voltage somewhere between 1 and 2 volts. So if you really want this to stabilize at 12 volts, you have to put closer to 13.5 to 14 volts into it, minimum. These can handle up to 30 volts of input voltage, or 35, depending on the component. But they have to have a difference of, just to be safe, let's say 2 volts. So if you want a 12-volt output, you really need to have 14 in here. I bet that if I turn that voltage on my power supply up to 14 volts, it won't turn off anymore. So let's see if I'm right. Okay, I've now upped the voltage from 12 volts to 14. So we have our 2-volt dropout voltage, right? I'm connected back to the power input instead of the battery input. And I'm going to go over here, and if I'm right, this will work now. Well, if I turn the power supply on, that is. Here we go. And there it goes. The meters are settled down, and everything is working. So what that means is that we have to install or use a little bit bigger power supply. Now I have a couple options here I can do. This is mine, and it's never going to leave my bench. I can have an external power supply like they did, or I can build a little internal power supply to run this thing and just put an actual power cord connector on there. Now, to me, this is not a piece of collectible antique. This is a usable piece of test equipment that I want to use on my bench. And it's not going to be a shelf queen. So I want it to work reliably for a long time. And while we could use external power supplies, there's two problems with them. Number one, the more switching power supplies I have, those little power brick things like this, the more RF noise I'm generating in my already noisy shop. Second of all, you got all these great big things hanging outside the back of your test equipment, and I already have enough of that. So what I think I'm going to do is I'm going to install a proper IEC connector on the back of the device. I am going to install a small power transformer that will provide the necessary voltage and turn this into an AC operated unit with its own built-in power supply. There's no RF or any kind of electromagnetic anything in here that will be affected by having a power transformer in here. So I'm not really worried about that. What I am worried about is making sure this thing works properly. Now, at idle, this thing draws about 355 milliamps. And I would have to say that if we're using the internal audio amplifiers for the monitor speakers and so forth, maybe this thing will max out at about a half an amp or a little bit over. So if I have a power supply that can that can produce a steady 1 amp current, I think it'll be fine. And if you look at the specifications for this, that's actually what they're asking for, is a 12 volt 1 amp power supply minimum. So that's what we're going to look at. Well, I think I found a suitable transformer. It's 24 volts center tapped, so that means we have 12 volts from here to here and 12 volts from here to here. And that's with 115 volts in. So at 120 volts in, it'll be a little higher. And that would be RMS. So we should have somewhere between 13 and 14 volts on each side. And that's exactly what we want. And the peak voltage will actually be higher than that, but we're not worried about that. We're going to have enough voltage difference from this to be able to properly operate that voltage regulator. So I'm going to mount that inside here next to the battery compartment, because there's all kinds of space in there and it'll fit in there very easily. You can see we have lots and lots of room, and we're going to make this work. And I think what I'm just going to do is put a standard 2-prong power supply on, or power cord on here. That's all we need, because the transformer is going to provide the isolation that we need. And the original unit was isolated as well. So this whole chassis is isolated from earth ground. And they do that on purpose. Once again, you want to keep this thing isolated the whole way. So that's what we're going to do. Okay, I removed the side handle assembly, and I marked and drilled 2 countersunk holes to hold these 832 screws, which will be flush in here. So when this goes back over there, that'll be hidden behind there. And then that will allow this transformer to mount on the other side, right onto these holes. And then I'm going to use these nylock nuts so that it never works loose. Alright, the deed is done, and it's not the way I like it to be, but it's just a function of how these Sencore from this era, how these Sencore devices are designed. They all have the external power supply, and when you plug them in, they have a transformer in them. They're linear supplies. They have continuous power on the transformer and on the capacitor and on everything. It powers this up, and the 12 volt regulator has power on it all the time as long as it's plugged in. It's just a bad design the way they do it. I would much prefer a regular power switch that cuts the mains power to the transformer, but I really don't want to deface this anymore, and there's really not a good place on the faceplate. The way it's designed, you can't really cut anywhere to put a switch. And without getting exotic with the designs, and there are ways to do this. I have equipment that I work on at work that uses a standby supply to drive a relay and then bypass, pull the mains into the transformer, all that stuff. But I'm not going to go through all that for that. This is my device for my bench. When I shut the bench off, it kills power to everything. So this will only be powered up when the bench is turned on. So it's not going to be an issue. Although, I don't like these designs. So this was a 24 volt center tapped transformer, and as such, I have a full wave rectifier using 2 diodes. So that's going to be 12 volts, because it's 12 volts from the center tap to either end. If you take 12 volts and you want to look at the peak voltage, first of all, that's at 115 volts mains. Here, our mains voltage is 120. So you're going to have closer to 13 volts RMS, not 12 volts on either side, which is going to be 26 volts, center tapped. So let's just say it's 13. If we take 13 times 1.414, that's going to be your peak voltage. That's like over 18 volts peak. So what's going to happen is when you plug this in, this capacitor, there's not going to be hardly any current draw on this other than just the regulator running over here. So you're going to have somewhere around 18 volts is what I'm going to predict is in here. And that's still good because these LM317s, you're good for at least 30 volts input they can regulate off of. The downside is the more voltage you're cutting on this, the more it has to convert into heat, because that's how these work. So if you have 14 volts going in here, you're only dropping 2 volts to get 12 volts out. If you put 18 volts in, right, you have 6 volts to drop. So it's going to add a little more heat to this. Now you do have this steering diode, which drops about 0.7 of a volt. So that's going to get us down in the 17 volt range, or just mid 17 volts. So long story short, this is going to work perfectly if everything goes as I just calculated, which I'm sure it is. So let's get the meter, and let me see if the camera can get a little bit better view here. How about that? Everything's going to fall, you know that. And I'm going to plug this in, and I'm going to get my meter probes here. And let's turn this on and just see what kind of output we have. Okay, so power is on. So this center tap is the common, and where the two diodes come together is going to be your positive. And it's even a little higher. I calculated 18.38. I got 19 volts, so that pretty much means that my mains voltage is a little bit higher than I thought. So if I look at this 28, so I have 14 volts. I said 13, it's 14. So it's a little bit higher. So long story short, our unregulated power right now is 19 volts. So we're dropping about 7 volts across this regulator right here, if I can get the camera at the correct angle. So looking at this regulator, where's my pointer? Right here, and you can see it's on a nice heat sink, and it's ice cold, but it's actually live right now, believe it or not. If we take the meter back, we should have somewhere around that 12 volts in there. So if I go from the common to the, I think the output is this side. Nope. Right there. I'm a little bit high. It's 12.6. 12.7, and that would be adjustable by this pot, which appears to be turned all the way down. You see it? See how the arrow is pointing? So, and I've read on some forums about this, that this is a known issue with these. That 12 volt regulator, I think the resistors that they chose, if you look here, for whatever reason, you have a 500 ohm pot and a 2.4K, kind of, this is your limit right here. This 2.4K should probably be closer to 2.2K. If we swap this out with a 2.2K resistor, we would be able to get a lot closer to, with the pot being in the middle of its adjustment, you get right around 12 volts. I would really like it to be more like 12.4, 12.3, just a little bit above, to allow for the drop in, all the connectors and wires and so forth. So I'm going to remove this power supply right now, and I'm going to recap it, because again, this thing's going to have power on it even when you're not using it. So we don't want these capacitors to leak or anything, because that really will mess up the board. They look to be in very good condition, but I'm going to start out fresh with brand new caps. So we're going to pull this board, recap it. I'm going to change that resistor from a 2.4 to a 2.2K, and then we're going to adjust it for the proper voltage, and we should be ready to go. Okay, I have all of the parts replaced. The capacitors, I replaced these pots because these little plastic ones, they're very, very loose, and they don't have a really long life expectancy for, number of rotations, their duty cycle and everything. And they tend to get noisy, and I don't want that to happen on the power supply. One of them controls the 12 volt regulator, which is this one right here. The other one controls the oscillator for the isolated plus and minus 5 volt supplies, so you can see it's right there. So I replaced both of those. I just took the meter and I measured the resistance of this one and set it to the same thing on this when I put it in. And this one really doesn't matter because I changed this resistor, the 2.4K, to a 2.2K, and well, we'll put it together and see if it works. Okay, hopefully I have everything in shot here. So let's plug this in. And let's look. Now, another thing I did before I put this in was, as you can see, I lifted up diode CR1, and where CR1 was, which is this one right here, I installed 2 additional diodes. So essentially right here, where that unregulated supply comes in, I have 3 diodes. And what that's going to do is that's going to give you about another 1.5 volts drop. So I'm going to have a little over 2 volts of drop. So that's going to take that from 19 volts down to about 17, 16, and that's where I want it. It would work the other way, but the less voltage you have to drop across this LM317, the less heat it's going to produce. So that's what I'm really looking for. So as you can see, coming in, there is, as we saw before, okay, didn't have my ground hooked up good. So I have a little over 19 volts going in, and on the other end of those diodes, if I can do this around the camera because I can't see, hold on a second. And just like we expected, 17 volts. That's good. That's right where we want it. Okay, looking at the voltage regulator, we have about 12.87 volts. And let's see if we can get that adjusted now. Because remember, that was about the lowest it would go before. Let's see if we can get on here. Wrong way, of course. And this pot turns backwards the way that I have it in there, but I don't really care. And like I said, I wanted about 12.3. That should be good right there. Alright, so this whole thing should run perfectly now. Now what we want to do is we want to look at our regulated voltages that are driven by this. So let's just make sure that that's working properly. Okay, turning the unit on, that brings up these isolated supplies. And this pot here should, I think that's what this diode is lifted for, so that you can see what the voltage is at the output. And I'll show you what I'm talking about here. So we're on this circuit right here. This is the pot. And this drives this oscillator that drives this little transformer, and then you have a bridge rectifier, and that provides your positive and negative voltage to go into here. And these are 5 volt, low current regulators. And of course, if you want 5 volts out, you need at least 2 volts more than that in. So I would imagine this is going to be somewhere around 7 or 8 volts. And they probably just have you testing from this to ground. Now this is a isolated ground. Notice this says R, and this side says L for right and left channels. And then if you go back here, these ones are on chassis ground. So they're common to this. So you have to measure these with respect to the ground terminal here, which is P5 pin 1. See there? So if I go from P5 pin 1 to that standoff diode, we have 8 volts. And that's what I expect. That's what I would have expected that to be. So that is correctly set. So now what I want to do is go from here to the positive and negative. So here's the positive 5 volts. That's really good. Negative 5 volts. Very good. And then for the other channel, same thing. We're going to look at positive 5, negative 5. Our voltages are good. So I think we're good. Now, the only other thing we have not tested is this charge pump converter and these 2 outputs here, and that would be on P4, pins 1, and these are all common ground, or chassis ground. And we can look at the minus, plus, and plus 12. So that's on P4, pins 1, 7, 5, and 6. All right, so P4, pin 1 is your ground. It helped to turn the meter on, wouldn't it? Okay. There's 12. There's 5. And there's 12. Let's see, where's the minus 5? There it is, minus 5. So those are good. All our power supplies are good. So I'm happy now. And now that we have these all set to respectable levels, none of these regulators are going to drop a huge amount of voltage. So they shouldn't run hot at all. They should just be room temperature, and they are. I mean, these ones are just barely above room temperature, if that. This is almost cool. This is just room temperature, and these are all cool. So, good power supply. All right, we're all put together, and I've been having just a little bit of fun messing around with this. And basically, if I had to describe what this thing is, it is a multimeter on steroids, along with a dummy load. So let me try to explain what all it can do, because it's quite a bit. And I'll probably miss some of it because there's so much you can do with one of these. It's a lot more than I actually thought it would be. The first thing is, don't let these analog meters fool you. They are extraordinarily accurate and sensitive. So much so that it'll keep up with the likes of, you know, a fluke meter or something. When you're in this scale right here, I'm on RMS voltage, and this will also read DC when it's in this mode. Anything that's in the orange area is you're reading these terminals here, and the dummy load, which will be either open, 32, 16, 8, 4, or 2 ohm, those great big resistors. And what it'll read is any voltage that's on these terminals will show up here, and you can see right now it's 0. It is extremely sensitive, and you can see things on here that you normally wouldn't see with your multimeter. So let's turn this on. And you can see, and it had to change scales because I have it set to auto scale right now. And you can set it on hold, or you can actually click this select, which is a momentary, and you can toggle through the different meter ranges. So it can be an auto ranging meter or a manual ranging meter. Now the amplifier's turned on, there's no signal, the volume is all the way down, and you can see we have we're in the times 0.01 scale, which is the minus 40 dB scale. So essentially what you have is 0.3 times 0.01, so that's 0.003. So that is 3 millivolts. What you're actually seeing is 3 millivolts of offset on the output of the amplifier. Pretty incredible, isn't it? Clear as day, you can see it. Now if that gets above a certain threshold, these will trigger. So for instance, if I turn this amplifier off, what will happen is the capacitors will start discharging, and one side of the push-pull of the outputs will turn off before the other, which for that split second you'll get that pop, that thump when an amp turns off, and that's DC on the terminals. This will actually trigger that. Watch this. There you go. And it triggered it because did you notice that when I shut it off, it showed that how that offset was on there. That was the speaker thump. And you can see right now with the amplifier off, there is still some residual noise on there, and that'll take a while for it to go away. And see, it's going to go through all of its scales. It's kind of toggling back and forth. And there you go now. And now the amplifier is completely powered down. So you can see without even connecting a test signal or anything like that, you can already see what's going on there. It would take me way too long to go through this whole thing, and I'm not going to do it in this video, but you're going to see this in future videos, and I'm going to use it on some future receiver restorations. But to give you just a quick rundown, these volume controls, there's these little tiny amplifiers built in with those little speakers that I showed you. And if you feed anything into here, you can actually listen to it through these speakers, which is really nice. So it's like a monitor, a built-in monitor. So you don't have to, if you're running the amp at 100 watts per channel, for instance, I can listen to it at a very listenable low volume just to hear what it sounds like. Of course, it's low fidelity, it's two little tiny speakers, but you can do that. If you look at these connectors, so any connector that has this little ground symbol, these are all connected to chassis ground. So the left audio input, so you can actually put an audio line level signal in here, like you can connect a tape deck or MP3 player or something like that, or come out of a preamp with preamp outs and test a preamp. That's what these are for, and they also will work with the monitor. These two inputs here are for the meter circuit. So this blue section, if you turn to, well, let's start. If we go to the yellow section, notice the yellow ring, they're color coded. So anything that's going into these terminals, you can measure with these sets. So you can measure the RMS volts, the dBm, or dB with reference to a milliamp, and dB program, which it means if you put it on this one and then you hit program reference store, then anytime you increase or decrease the amplitude of the signal, it'll read out the difference on the meter. Very, very cool. This can also, these inputs, which is the blue section, acts like a multimeter. So it can read RMS volts, it could read just straight DC voltage, it can read, so for instance, if you wanted to see if there was like a DC offset, with signal riding on it, you can look at the offset. Or if you just wanted to look at the AC voltage, you could do that. dBm, once again, so you're measuring the voltage with in dB with reference to 1 milliamp, I'm sorry, or milliwatt. I'm speaking out of turn here. And it shows you even down here the input impedance. So when it's AC, it's a 1 mega ohm input impedance, and with DC, it's a 15 mega ohm impedance. So if you want to look at DC offset or a very small DC level, this is the same as a multimeter. Multimeters can be anywhere from 10 to 30 mega ohms input, depending on the meter. Most of them are 30, like these Flukes. So 15 meg, that's not bad. That's a pretty high impedance. So that's what all this is for. And again, you can listen to whatever's on this terminal through the speakers once again with that little built-in amplifier. And you saw the DC offset protection kick in. So it has its own speaker protect circuit as per se. And all it does is it'll disconnect the load from the input if it sees DC offset. So these input filters, these are for the meters. They're not for, they don't filter the signal itself. They filter the amount of signal going to the meter. So for instance, if you put it on bandpass, it will only show you anything that's between 200 hertz and 15 kilohertz. It'll roll off on both sides. So the meter will only show you that frequency range of audio. Same thing with high pass. Anything above 200 hertz, the meter will react to, but anything below 200 hertz, the meter will ignore. And this is low pass. Anything below 15 kilohertz, the meter will pass. Anything above it, it will block. So as you can see, this thing can do a lot. It's very cool. And I'm still learning it, and well, it'll show you wattage. So let me connect something. I'll show you that, and then we're going to wrap this video up. Okay, this is not a real good example because I have a loose connection on this RCA plug that I'm using from my signal generator. So if you see some meters jumping around, it's my test equipment. It's the cables. It's not this itself. So I have the volume up, and you can see right now it's on 1 per, times 1. So for instance, you're at right now, you read this bottom scale. If I go right here, there's 5 watts per channel. You see that? We're on 5 times 1, 5 watts per channel. And if I come out of these two things here into the scope, it lets you actually monitor the waveform. And it is scaled properly as well. And the scaling on it, you have to read the instructions how it works, but there is scaling to it, so it's accurate. It's not just a representative waveform, but it actually has a scale to it for amplitude. And it's just as simple as that, and I can actually watch the scope here and take it into clipping. Right now it's clipping. So I'm clipping, according to this, at about 20 watts per channel, which is correct because this amp is rated, I think, somewhere between 15 and 18 watts per channel or something. So it just makes it so easy for anything you want to test on an amplifier. So I'm really looking forward to using this. It's pretty exciting. And, well, you're going to see it in future videos. I have quite a few coming up. So I have one that I think I want to do next, that famous last words. It's supposed to be mostly functional, maybe just need recapped or something. It's a fairly valuable receiver, so it might be worth doing a recap on it and so forth. But famous last words, things come in and it says that they're supposed to be working and everything, and then you find that it really doesn't work. So who knows how that's going to turn out, but we will definitely be using this on it. So until next time, I wish you all peace, joy, happiness, and good health in your lives, and we'll see you again real soon. Take care, everybody. Bye-bye.